These are the notes for Operations Research Week 1 Monday. It's on linear programming. We start with an example 1.11, and it reads, a company makes hats and shoes. It can make $10 for each hat it sells and $20 for each pair of shoes it sells. Let x1 be the number of hats it produces in a month, and let x2 be the number of pairs of shoes it produces in a month. Supply constraints require that x1 be less than or equal to 150, and x2 be less than or equal to 150, and x1 plus x2 is less than or equal to 200. Set up a linear program to model the situation and to try to solve it graphically. The first step is to find the objective function, which I labeled here. It is a max problem because you want to model it. Sorry, words are hard. It's a maximization problem, and you get our constraints from the very first part where it says you can make $10 for a hat and $20 for a pair of shoes when it's sold. Then you find your constraints, which are nicely labeled here in the problem, and that's what your equation is subject to. You also have your non-negativity constraint, which are x1 and x2 are greater than or equal to 0. Since you're solving this graphically, then you move over to the graph and you label your constraints. We have x1 is less than or equal to 150, and x2 is less than or equal to 150. Then you have x1 plus x2 is less than or equal to 200. So there, and there. So down here is your feasibility range because you want to see what the maximization is. The feasibility range is this entire area here. So then we need to set to figure out what is the best solution. So we have 3 points. We have here, 5 points. Don't know where I got 3 from. So 1, 2, 3, 4, and 5 down here. We know 0, 0 won't give us the best answer for the maximization, so we just kind of get rid of that one. But then we plug in 150, 0, which gives us the equals 1500, 150, 50, 50, 150, which you get 3500, and right here we get 0, 150, which is 3000. So our best answer is here, 3500 with 50, 150. Next we have a question. What are the binding constraints in the optimal solution in the previous question? What happens if we change the right side to the binding constraint? So x2 is less than or equal to 150, and x1 plus x2 less than or equal to 200 are the binding constraints. That's because here, if this changes, the answer would shift. And here, if this changes, the answer would shift, because this is our point that's best answer. The optimal solution occurs at the intersection, here. Not much will change if you change this binding constraint up or down. The next example is on the back page. It's a preview of the simplex algorithm. Oh, but first there's a question. Almost skipped it. My bad. How can we turn an inequality like x1 plus x2 is less than or equal to 200 into an equation? So we take x1 plus x2 is less than or equal to 200, and we make it s1 plus x2 plus s1, which is a slack variable, is less than or equal to 200. And that is how you make it an equation. Next we go to example 1.15, which is a preview of the simplex algorithm. And we write down the starting standard tableau in linear programming form from example 1. So here's we set up the tableau, and we find the most negative up top. So this is our entering value down below, and that's what we want to put here. For the ratio test over yonder, which you also have to do up here to find which value you wanted to change. Move down to the second tableau. Same thing again, find the most negative here. Find the constraint you want to change here, and go down. According to this, our optimal solution is 3500, given from the first row. S1 would be 100, which is our slack variable. X2 would be 150, and X1 would be 50. Now if we refer back to the first problem where we solved it graphically, you'll see that is the answer that we got. Solve the same way. So the object coefficient of S2 is 20. The profit will increase by $20 if you increase the slack constraint by 2 by the limit. The object coefficient of S3 is 10, and the profit will decrease by 10 if you increase the slack of the constant 3 by 1. Lastly, we have this last example. It reads, consider the linear program in example 1, and suppose that the objective coefficient C2 of x2 in the objective function can increase or decrease by a real number alpha. What values of alpha cause a change in the current bias of the optimal solution? So we have x2 equals negative 10 over 20 plus delta, x1 plus x star. I'm sorry, I don't know if that's a star or squiggle out. And then we go down to negative 10 over 20 plus delta is greater than 0. Change a little more, negative 10 over 20 plus delta less than or equal to 1. Until finally you get negative 10 is less than or equal to 20 plus delta. And finally, negative 30 is less than or equal to delta. So we move over to the graph and we graph it. Same graph as from before, but you see our feasibility range has shifted some. So the basis will remain optimal provided that delta is an element between negative 30 and infinity. If delta is less than negative 30, then 150 to 50 will become the optimal solution. So this is how we would change the optimal solution from what we originally found.